Right, hello everyone. I'm Srishti Sathat. I am a PhD student associated with the Center for Systems and Control at IIT Bombay, and I am also the TA for this course, W98. So, welcome to the fourth week tutorial session. Let me just correct this. Yeah, so let's get started. So, let's start by recalling the concepts that were done in this week. So, this is going to be the overview for today's session too. So, overview. So we'll be mainly talking about stability analysis. So first of all, we'll discuss about eigenvalues and eigenvectors. Then we'll talk about positive definiteness of a matrix. So these are the prerequisites to determine stability of a system. Definiteness. Wait. So we'll use the criteria proposed by Sylvester. And then we'll talk about stability of LTI systems. So we'll talk about bounded input, bounded output stability, asymptotic stability, asymptotic, and then finally stability in the sense of lack. Right. So first, let's begin with determining eigenvalues and eigenvector matrix. Yeah, sure, I'll do that. Once we get to that topic, I'll describe it. Okay, so matrix of a matrix. Alright, so you must have learned to determine the eigenvalues. What we need to do is calculate the determinant of Si minus A or lambda I minus A and equate it to 0. So the solution lambda i's I ranging from 1 to n would be the eigenvalues of the matrix. So let's begin with an example. So it's a 3 by 3 matrix. -4, 1, 0, 0, -3, 1, 0, 0, -2. Alright, so let's first calculate lambda I minus A. So that would be lambda plus 4, lambda plus 3, lambda plus 2. So the determinant would simply be determinant of lambda I minus A. You can expand to this column. So this is simply going to be lambda plus 4, lambda plus 3, and lambda plus 2. Equated to 0 and we get 4 distinct eigenvalues. Sorry, 3 distinct eigenvalues. -2, -3, and -4. Alright. So if these are distinct eigenvalues, we can find the eigenvectors for this. And this is the simplest case. So let's see. So eigenvector, for example, for lambda equals -2. So what's the equation? It's A operating on the eigenvector V equals lambda operating on B. Or in other words, you can say that A minus lambda I V equals 0. So we want to find V, which is in the null space of the matrix A minus lambda I for a particular lambda. Alright, so we already have A minus lambda I. Let me just write this. Minus for minus lambda. So just the diagonal elements would change and the rest of the entries of A remain the same. This is A minus lambda I. And for lambda equals -2, we have -4 plus 2, -3 plus 2, and 0. So the vector V would be a 3 by 1 vector. So let's name the components. Let's say it's V1, V2, V3 equals 0. And the objective is to determine this vector V. Alright. So let's see. So you can observe that this entire row is 0. So we just have two equations in three unknowns. So let's write down these equations. This would be -2v1 plus v2 equals 0, -v2 plus v3 equals 0. So these are three unknowns and two equations. Alright, so let's assume a value. Let's say that this implies that v2 equals v3. So we can assume some value for v3 and that would be equal to v2. And now we need to determine v1. So let's say v2 is to v1, which implies v1 is half of v2. So given any value of v3, v vector would be half of v3, v3 and v3. Half, 1 and 1. Which one of the choices could be half, 1, 1 for v3 equals 1. So this is the set of all eigenvectors corresponding to lambda equals -2. Alright, so let's see for the other two eigenvalues. Yeah. This is true for lambda equals -2 because we have substituted lambda equals -2 here. Yeah. Yeah. Okay, so what kind of other assumptions do you mean? Because what I could do is simply mean V3 equals some constant K and K could be. Yeah, constant. Yes, it's the same procedure. If the eigenvalues are complex, you can do the same procedure for the roots. For lambda equals -3. Okay, so I'm just going to write down a minus lambda I for lambda equals -3. So this is -1, 1, 0, 0, 0, 1, and again 0, 0, 1. Operating on V1, V2, V3 equals 0. Okay, so you can observe that these are going to lead to the same equations, which is simply V3 equals 0. And then the first equation is minus v1 plus v2 equals 0, which implies v1 equals v2. Let's say some constant c in R. So then what do the eigenvectors for lambda equals minus 3 look like? This is some k, and c2. So you can just take the simplest case, k equals 1 implies 1, 1, 0. Alright. Then we have the last case for lambda equals minus 3. Sorry, minus 4. Yeah, minus 4. So it's, let me go back. Okay, so this is a minus lambda I. So this is going to be 0, minus 1, and sorry, 0, 1, and 2. 0, 1, and 2. And the rest of the entries of A. So this is 1, 0, 0, 1, 0, 0. Alright, so this equation is the simplest, which simply implies 2v3 equals 0, which is v3 equals 0. Then we have v2 plus v3 equals 0, which implies v2 equals 0. And then v1 can be anything. Any constant c. So the eigenvector is c0, 0. And for the simplest case, this is 1, 0, 0 for c equals 1. So I hope that this example was clear to you. Now let's move on to some questions. Right. So find the eigenvectors and eigenvalues for the following matrices. So the first one is A equals 1, 1, 0, 2. So only two eigenvalues, that would be a simpler case. So the characteristic equation is, let's say this is A minus lambda I, determinant equals 0. Alright, so this becomes 1 minus lambda, 2 minus lambda, 1, 0. Determinant should be 0. This implies the eigenvalues are 1 and 2. Okay, so these are distinct eigenvalues. So we can perform the similar procedure as in the example. These are distinct. Okay, so let's see for lambda equals 1. A minus I acting on B equals 0. This is in R2. Alright, so this becomes 0 and 1. Which is simply v2 equals 0 and v1 can be anything, any constant. In the simpler case, it's a unit vector 1, 0. So all of the eigenvectors such as 1, 0, 2, 0 or in the positive direction or here. These are all eigenvectors corresponding to lambda equals 1. So note that you cannot put c equals 0, so c should be non-zero. So non-zero vector that satisfies this equation, right? So B cannot be a zero vector. All right. So similarly for lambda equals to it's going to be -1, 0, and 0. All right. So in this case, this is simply minus V1 plus V2 equals 0. V1 equals V2. Let's say some constant C. So the eigenvector is or a multiple of the vector 1 pi. Alright, so let's move on to a bigger matrix. A equals 0, 1, 0, 3, 0, 2, minus 12, minus 7, minus 6. Alright, so the characteristic equation is A minus lambda I, determinant should be 0. Alright, let's see. So this is minus lambda, minus 6, minus lambda. Alright, so this is 1, 0, 3, 2, minus 12, minus 7. Determinant of this equated to 0. Alright, so let's see. This is going to be minus lambda. Plus 14 minus 1 and then minus 12 lambda. So let me know if the calculations are incorrect. I'll change them. Let me just check this once. Minus lambda. Where? Okay, so this one, right? Okay. Next, that is plus. Yeah, alright, thank you. Okay, so let's just expand this quickly. Okay, yeah, so this is just multiplication. This is this. Yeah, okay. So let's expand this. This is minus lambda. Okay, so this is let me just write this in a standard form. So this is minus lambda cube minus 6 lambda square minus 14 lambda. Just 1 second. Plus, right? It's this one minus of minus 2. Yeah, yeah. Okay. All right. This is minus 1 and then minus 3 lambda plus 6. Let's see. Well, then let's calculate just one so that we don't have to do it again and again. Let's see. Minus lambda cube Okay, so see if this is correct. Yeah, that's true. So you can always use solvers. That's fine. Mm, yeah, all right. So let's check if we can solve this. Um, yeah, all right. So lambda plus 1. Okay, is lambda cube plus lambda square. Then 5 lambda square plus 11 lambda plus 6. Then also 6 lambda plus 6. Okay. So this is lambda plus 1. Lambda square plus, sorry, 5 lambda plus 6. So solving this is minus b. Okay, so we have real roots. So this is minus 1 plus 1, 2. Minus 5 minus, this is minus 2 and minus 3. Okay, so the eigenvalues are minus 1, minus 2, and minus 3. Okay, so these are distinct eigenvalues. You can easily solve for the corresponding eigenvectors. Okay, so we are not going to do that computation. If you are interested, you can go ahead. So compute the eigenvectors. You can also check the eigenvectors from your computation and from any of the softwares, maybe using MATLAB. That would be a good exercise. Alright, so let's move on to the next point. So this is the stability analysis. So stability of state space models or systems. Stability of Alright, so let's begin with the question. So I think this is the second one. Yeah, question 2. So I'm going to write down the matrices for the state space system. This is 0, 3, 1, 2, 8, 1, minus 10, minus 5, minus 2. Then B is 10, 0, 0, and C is 1, 0, 0. Question is to find out many poles or eigenvectors are in the left half plane. Now in the left half of the S plane, in the right half of the S plane, and on the j omega axis. Okay, so I'm going to give you a minute to think about this. Just a second. Sorry, can you just write down your comment? Mm. Okay. I see. So have you calculated the eigenvalues of the pose, or have you used some other test? Mm. Okay, let's see the question. Okay, so let's see. Suppose all eigenvalues. Okay, so let's first find out what is A minus lambda I, because we have to talk about the characteristic equation. So this is minus lambda, 8 minus lambda, minus 2 minus lambda. Right. So characteristic equation is of A minus lambda I equals 0. So let's compute this. This is minus lambda. Okay, just check this once before we move on. So this is alright. So let's simplify this. Now we have plus 5, and then this is minus 4 minus 2 lambda plus 10 plus minus 10 plus t minus 10 minus. Alright, so this is lambda square minus 10 lambda minus 11 minus 10 lambda plus 7. Okay, then we have plus 6 lambda minus 18. Okay. So this is minus lambda cube plus 10 lambda square. Okay, so then we have plus 7 lambda. Yeah, that's it. And then we have 70 minus 18. So 2, and this becomes 2. Alright, so we can, this part is the characteristic polynomial without equating it to 0. This one? Okay. Okay. No, this is minus 8 lambda. Okay, fine. Yeah. Yeah. This is minus 8 plus 6, right? Yeah. Oh, sorry. Yeah. Plus 2. Yeah. Minus 6. All right. So let's. So it's minus 6 lambda. Yes. Is this all? Okay. Just let me know if there are any more corrections. So. This becomes plus 6 lambda square. Okay, so this is minus lambda cube plus 6 lambda square plus 7 lambda plus 52. Okay, so this part, without equating to 0, is the characteristic polynomial. So there are two ways to know if the location of the poles. So one is actually calculating the eigenvalues of the poles by equating it to 0, or we can also use the route criterion, right? So these are the two methods. So one is finding roots of this equation. Or second, by the Route-Hurwitz criterion. So let's take this approach so that we don't have to actually find the roots of this equation. This is a third order system. So let's see lambda cube, lambda square, lambda 1, and that's it, lambda to the power 0. Then we have minus 1 plus 7, 1 plus 6, and 52. Okay. So can you tell me the rest of the entries? What's this one? So this is from 6 into 7. It's minus 52. I hope I'm right. Yeah. Divided by 6. So this is 42 plus 52. And then we have. Okay. I hope I'm right. Just a second. So I'm just going to write this down. Sorry. Okay, so let's see. What else we can do is just simplify the lambda square part. So divide by 3. So this is divide by 2. So this is 3 and 26. Alright, so this makes it simpler. Lambda 1 would be, just scaling this down, then lambda 1 would be 47 over 3, 0, and lambda 0 would simply be 26. Sorry. Okay. So I'm just going to rewrite this. This is lambda cube, lambda square, lambda 1, lambda 0. Now to determine the number of poles in the left half of plane or the right half plane or geometric axis, we have to determine the sign changes. Alright, so there's just one sign change here. That's it. Okay, so this means out of the 3 poles, because it's a third order polynomial, there is just one sign change. So there is just one stable pole, which means one pole in the LHS. And then we have, sorry, 2 poles. And one unstable pole, which means it's the RHS. And then note that there are no poles on the j omega axis. This is the rule. Sign changes equals to number of poles in the RHS. Alright, so I hope that this was clear to you. Now let's move on to another topic. This is positive definiteness. X. So let's see. So if we have a matrix P, then how do we say that it's a positive definite matrix? So let's say that P is some square matrix. And then we say it's positive definite if X transpose Px, this is greater than 0. So X is any vector with n dimensions. So X transpose X would be a scalar, right? This would be 1 by n by n, and then X would be n by 1. So this means it's going to be a scalar. So if that scalar is positive, we say that P is a positive definite matrix. Alright. So there are 3 criteria. So if a matrix P is symmetric, then there are no, that's not the case. But there could be a larger class of matrix because we could have some negative elements, but this expression should be positive, and that should be true for all vectors x. Alright, let's see them first. So if a matrix is symmetric, then we have 3 criteria to determine positive definiteness. No, X transpose Px, depending on P, could be less than 0, equal to 0, greater than 0. If this is positive, then P is positive definite matrix. Sorry, this is only for if P is symmetric. So instead of checking for every vector, every n by 1 vector, what we can instead do is determine its determinant, If this is greater than 0, then the matrix is positive definite. If the eigenvalues of P are real and positive, symmetric matrix P is positive definite. And then finally the general rule, X transpose Px should be greater than 0 for all vectors X in Rn, and this scalar is allowed to be 0 if and only if X itself is 0. No, we are not talking about 0 matrices. This has to be at least greater than 0, so that cancels that case. Alright, so we have just seen that X transpose Px is a scalar, so let's name that scalar. Depending on some vector X, B of X is X transpose Px. That's right. Alright, so based on the positive definiteness of P, we have some criteria on B. So Vx is first positive definite, then X transpose Vx is greater than 0. Again, the same statement for X non-zero and Vx equals to 0. This is if and only if X is the 0 vector. P is not a 0 matrix. Then the function B is negative definite. X transpose Px is less than 0. Then it's no, because X could be any vector, right? If X is, for example, minus 1, 1, then some element of the matrix P could be negative to make this whole scalar positive, right? So X could be any vector, that's the point. So I'm going to write this down. This is positive semi-definite. This is when X transpose Px is greater than equal to 0. And similarly, negative semi-definite if X transpose Px is less than equal to 0. Alright, so let's see an example. X plus x1 squared plus x2 squared. So we know that this is always greater than 0 for the vector x written like this to be non-zero. Okay, so what's P in this case? So we have to write it in this form. So you can see that there are no mixed terms x1, x2. So P must be diagonal, right? So this is x1, x2, sum 2 by 2 matrix, x1, x2. And the coefficients are 1, so this is simply 1, 1, simply 0. The identity matrix of size 2. Alright. So if it's a bigger matrix, okay, so for example, if it's x1 squared plus x2 squared plus alpha, let's say x1, x2, let's say that we can write this in terms of some vector, let's say p11. So we just have to determine all the elements of the P matrix. That's easy, right? We could do this. Then the second element, P12 x1 plus P22 x2, and then this. This is p11 x1 squared, x1 x2. Okay, so it's a lot of terms now. Let me just write this down. So this is, yeah, p11 x1 squared plus p21 x1 x2 plus p12 x1 x2 plus p22 x2 squared. And now you just have to compare this and this. Alright, so let's see if we can do this. So p11 is simply 1, p22 is message 1. Then we have p21 plus p12 equals alpha. Alright. No, you can, I see. It might not be positive, so that depends on this. So what you could do is, if you have to construct the P matrix, you could fix one of them. Maybe this is 1, and there is some value of alpha, let's say 2. So then in that case, P21 is 1, and then you can construct the P matrix and comment whether that matrix is positive definite or not. Right now, at this stage, this is not enough to conclude the positive definiteness. This is clear. Okay. Let's see another example. Just 1 second, let me check. Why is this over here? Just a second. Hmm. Okay, if this ends, then we'll just rejoin this link. I hope that is fine. But we'll see at the end of, I think, 10 minutes or so. Okay. So let's say Vx is, this case is x1 squared. Sorry, it's x1 plus x2 whole square. Okay. So let's see if we can expand this. Is x1 squared, x2 squared plus. You can rejoin on this one. I'll also do the same. That's it. Plus 2x1, x2. Alright, so let's see if this is. So we have to comment on whether this Vx is positive definite or positive semi-definite. Okay, so let's see. Okay, so if we can write this as a matrix. So let's check when is V0. So it is x1 plus x2 whole square should be 0. So this is not true only for this vector, right? This is also true for x1, x2 equals sum minus c plus c. In that case, that could also be 0. So it is not positive definite. So let's check the criteria for positive definiteness. This is it. It should be greater than 0 for all x non-zero. And otherwise, if it's 0, the only possibility is that the vector itself should be 0. So this is not our case. I think we are. So we know that the square is always going to be positive, but in our case, it could be greater than equal to 0. X1 x2 equals minus c plus c. This is just one case. V of x is also same. So the answer is that Px is positive semi-definite. Alright, so I hope that this was clear to you. Let me know if it's not. Let's see. Okay. So Vx in this case is minus x1 square minus x1 plus x2 whole square. And this is, let's expand this. This is minus x1 square this is simply minus x2 square minus 2 x1 x2. Okay. Sorry. An additional term of minus 2 x1 square. Okay, so we could write this maybe in the terms of a matrix. So let's see. x1, x2. So it's minus 2 and minus 1 just by inspection. And this would be minus 1 and minus 1. Okay, so this is the matrix P corresponding to this function v of x. And now let's see if P is positive definite or not, right? Because we have to comment on the definiteness of V. Alright, so let's see what are the one second. This is minus, this would be fine, right? This is equal to this. Yeah. So in this way, in this case, we could do this, but in a higher dimension case, we might not be able to write this just by inspection. Alright, so definiteness of Vx depends on definiteness of this matrix P. And let's see. So this P is symmetric, right? P is P transpose. Therefore, we can choose any of those three criteria to determine the definiteness of P. Let's see. This is a second order system, so let's compute eigenvalues of P. We could also do determinant of P. So this is simpler. So determinant of P is, no, in this case it is. And for most of the cases that we are going to encounter in this course, P is going to be symmetric. So we are going to talk about P, which are symmetric, and then we're positive definite. So this is 2 minus 1, which implies that Vx is positive definite. So you could either write Vx as positive definite, or you could also write this, which means that it's positive definite. Right. Okay, so let's see the example of Vx, which is x1, x2 plus x2 squared. Okay, so the vector in R2 is x1 and x2. So how to use the positive definiteness to comment on the stability? That's what we're going to do next. Okay. So this is the vector. And to comment on the positive definiteness, we are going to construct some matrix P. So what we can do instead is just check the region where V is positive definite, right? It might, because x2 squared would be, for example, less than x1, x2, and x1, x2 could be less than 0. So in that case, Vx would be negative. So let's find out the region Vx is positive. Okay, so that could happen in many ways. This is the x1, x2 plane. x2 squared is always going to be positive. So x1, x2 is going to be positive in this spot, right? So we can actually impose a condition that Vx is greater than 0 for x1 greater than 0, x2 greater than 0. And just check once if Vx is 0, which implies that x1, x2 plus x2 squared equals to 0. So you will have to solve for. So this happens when x2 equals 0 and x1 equals minus 1. Mm. Sorry, x2 squared, right? Hold on a second. Something is too common, right? This is fine. No, no. Okay, sorry. So